周四，
有点长，这样。
下周会
也行吧。
下周
你下周 prefer 什么时间？
跟我们一样时间哦，周一那个。
可以吗？下周一的课后可以。我们这周也可以。对，我们这周自己 meet。啊，行吧。
Where's the rest? Holiday? Ah, right. Yesterday we had a holiday. But we haven't seen Joel and Hao Tian for a long time, right? You sick? Very sick. Oh yeah, I know. Okay. Okay. Yeah. You also sick. Okay. So you guys both meet, is it? Where do you get your sickness? No. Justin also sick. Justin is also sick. Okay. Before we start, I want to make this announcement here. So next week's Monday, right, 3:30 to 4:30, we have a seminar guest. It's my guest. Okay. Edmund. So he will give a research talk here, and then he will be visiting here for 3 days, Monday, Tuesday, and Wednesday. I will invite him to our class also, to share about his research experience. Okay. He after graduated, we split. So I mean, basically, we are classmates before, from undergrad, and then for PhD we have the same supervisor, and then after graduation, we split. So I came to SMUM here. So he went to IHES for 3 years, 2 to 3 years like that. And then he was moving. He's moving to Sydney now. So he's a postdoc in Sydney. Yeah. So he will be coming from Sydney. I recommend all of you to come. Okay. Maybe you will see some connection with algebraic geometry. Maybe it's not apparent from his talk, but I can assure you that whatever he did here very closely related to algebraic geometry. Yeah, there's a connection. And I recommend the 2309. Yeah, I recommend the 2309 students to come also. Okay, because in particular, you guys need to like find FIP, right? Okay, so if possible, maybe we can make connection with him. Okay, do some topic that he do. Yeah. Does it make sense? Yeah. Okay. Another thing is we might have a dinner after the seminar. So if you could join, you can let me know. In particular, if you got car, okay, maybe you can let me know also. Then we can arrange the transport easier. Hopefully if we have dinner or you have a chance to meet with him, right? Maybe try and talk to him. Yeah. What's the current max happening and what are the possible question or possible uh, problem again that the frontier mathematician are interested in. Yeah. Does it make sense? Okay. So if you have a chance to come, you try to come. Okay. We'll try and organize a dinner with a speaker. Yeah, maybe I'll bring him around here. Yeah. Okay, so please let your classmate know. Ask your classmate to come to the research seminar. Okay. I think most of you here seldom appear in the seminar, right? Is it? Did you went to do you know that department has a seminar regularly? Hmm? Do you know? Did Munir post something in your group or not? Huh? You guys in the XMUM mathematics department, you rarely see, right? Okay. Yeah. So Munir always will post there. So it's recommended you come to the topic you like. Yeah, so that you can develop your interest and then you'll know what happens in the research field. Okay. Yeah. So your calculation, all the maths you did is not just for the set of calculation. Okay, it's because people want to solve some problem. Okay, so that's why they're invented. Okay. Okay. This is for the research part. Okay, so as promised last time, we have to finish affine variety and projective variety today. Okay, so let's start with some summary here. Okay, let's give you a broad picture what's happening now. Okay, so let's start with algebraic set. Okay, so there are two kind of algebraic set we are looking at. One is affine. Okay, one is projective. Okay, so one is affine, one is projective here. Hey, what happened to my display here? Let's call it VP for now. Okay, and then through Hilbert's Nahr-Steller-Zach, right, you know how to go from zero set to ideal, okay, and then back from ideal to zero set. Okay, so similar happening in a projective case, but we replace ideal to be homogeneous ideal in this case. Okay, because we want the whole line, okay, to stay inside the zero set. If one of the point on that line is in the zero set. Okay, and important thing here is there's no The weak noun stellenza in the projective case is kind of different, right? We have a non-trivial ideal or non-proper ideal. Okay, that give you empty set. I mean, that gave you a zero set as an empty set, which we call the irrelevant ideal here. Okay, but when you apply IZ to an ideal, what you always get is a radical ideal of J. Okay, and then how about Zi on a zero set? You always get the Zariski closure. Okay, this is how we define it in our tutorial. Okay, I hope that you do the tutorial. Okay, if you don't do, at least you need to read it. Okay, so those are the supplementary material to our lecture. Okay, it's not enough to just prove whatever we did in the lecture. Okay, so we need to do expansion a bit. Okay, so maybe I need to explain a bit the difficulty of my assessments here. So, so after lecture, right, we should build on tutorial. Okay, after tutorial, we should build on assignments here. Okay, so these are the difficulties. So it get difficult, even more difficult, right? So that's why you have time for your assignment here. Okay, typically one week or 1.5 week actually. Okay, but so for our final exam, right? Okay, you are allowed to bring a cheat sheet. Okay, A4 sided. Okay, double sided. So I plan to include everything probably out to this week. Okay, meaning everything out to projective variety here. So how about the new topics then? Okay, so for the new topics, right? I want to do it seriously also. Okay, maybe we will put it as we'll term it as a bit like a take-home exam like that. Okay, but I guess it's very similar to assignment uh, method, but just that the difficulty I might increase a little bit, even a little bit more. Okay, see how I think because how many assignment we did already? 4 assignments, right? Okay, so those are the split of the 2 assignments, right? Okay, I split them. Let's see how it goes. That's what I think. Because you have to expect that when we go into singularity and divisor, right, these topics are actually harder. Okay, so since they are not in the proper exam hall, I don't ask you to do 2 hours there, then you should at least even more time to do it. But still, you can look for reference. It's not that strict. Just that I want to say that difficulty, the difficulty is increasing. Okay. Then where's the difficulty of test? What do you think? What do you think? Huh? No, not true. Actually, not quite true. Actually, not quite true. Test actually is around here because you have limited time. Okay, maybe a bit less than assignment. Less than assignment. Okay, because we have limited time. Does it make sense? Okay. Yeah, this is always what keep in my mind when I design the difficulty here. Okay, so it's natural that you feel that assignment is hard. Okay, because it's built on what we have learned. Okay, make sense? Okay, okay, so let's come back again. I made a exam announcement again when it close to the time. Oh, before that, how about presentation? You're supposed to meet with me this week, right? So I recommend that we move to next week. So it's the usual time meeting next week. Is that okay? For all the groups. Okay, usual time meeting next week. Is that okay? Yeah, so this week you can meet yourself first. I think by next week we also have to discuss around what day we should do our seminar. Maybe you can have a discussion within your first. Some possibility is at night, evening, or weekend. Yeah, because we don't have much choice here. In particular, you guys are from different classes, right? You have different ME. And then, yeah. Let's see how it goes. Okay, you can try and ask your group mate first. Yeah, I think Hao Tian haven't sent your group subtopic, is it, to me in the Teams. You look at the team chat, check the team chat. And I have returned you the assignment too. So I posted out the solution as well. If we have time, we can discuss later. If not, please read your solution, my feedback. Okay, and then if you don't understand, you can then ask me. Okay, so where are we just now? So we talked about Huber Selenzak here. And then inside this Huber Selenzak come with package one. So we can describe about radical, prime, and maxima ideal. Okay, so these are corresponding to algebraic set, irreducible algebraic set, okay, some variety, or maxima, okay, points. In affine case, in projective case, we have similar things. We also have radical, ideal, prime ideal. Okay, more importantly here, there's an irrelevant ideal here. So actually, we can go between projective set, okay, and affine set here. So if you start with projective zero set, right? Projective algebraic set here. Okay, that's mean your point are coming from homogeneous ideal here. But homogeneous ideal is a perfectly good ideal in the ring, polynomial ring. Okay, so meaning what? You can also view it as a ideal in a normal, okay, normal polynomial ring. In that case, you will have a affine zero set. Okay, affine projective set. But what's the relation between these two? Actually, not much. Okay, just that when you consider that homogeneous ideal in the affine case, you get an extra zero. That's it. Okay, did we prove this? I think we didn't prove it, right? We defined it, but we could, in principle, define something called con. Okay, and ensure that it is an affine. But it's not hard to check. Okay, it's not hard to check. Okay, given that you start with a homogeneous ideal, it's not hard to check. Okay, actually, you just exclude 0 point here. Similarly, then let's say if I start with VA, is there a way to go to projective algebraic set or not? Is there a way to do that or not? Okay, actually there is. Okay, actually there is. So let me give you one example. Okay, let me give you one example here. So let's say if you look at the V of S squared plus Y squared. That's one. Okay. So well, I mean this is a perfectly good unit circle in R2, right? Okay. But I can see that this polynomial here is not homogeneous. Okay, it's not homogeneous. So how to make it homogeneous? I haven't set out the question yet, but I think one of the proof we discussed it already, right? So if you consider x over z squared plus y over z squared equals to 1, for example, well, this is just x squared plus y squared equals to z squared. Okay, in that case, you can look at v of this guy here. But what is the v of this thing? You want to know or not? Ah, a corner. A con. This is what you learn in your AAG and your calculus too, right? How to draw this con like this. Okay. Well, in this case here, what's the axis here? So let's say this is a point. Then here, here, that, that, like that. Okay. But in the let's say this is a projective case, then we won't include this 0 point, right? We will admit this 0 point here. Okay. But can you realize you have this circle actually sitting inside this point? when z equal to 1. Okay, so meaning what? If you go from function, non-homogeneous function here, okay, you homogenize it, and then you look at certain slice. Okay, for example, z equals to 1 here. Okay, z equals to 1 is what in R3 here? It's a plane, right? Okay, it's a plane with height 1. Okay, so you look at this intersection. Then you recover your affine zero set. Does it make sense? Okay, so you can see that your affine variety here is sitting inside a table. Okay. Okay. Okay, so these things are really connected. We can go across depend on how we want to see them. Okay. Right. And then yeah, okay. So next is about function between variety. Okay, so similarly, I split it into two parts here. So there's a geometry part and there's the algebra part. Okay, so in the geometry part, we will have a polynomial map. Okay, so these are the polynomial map. Okay, between variety here. So you can note that actually we could define this polynomial map on affine space first, and then we restrict it to variety. We restrict to variety here. Such that when we have this function, right, in each coordinate in AM in the codomain here, actually it is a element in the function in the coordinate ring of V here of your codomain, sorry, of your domain here. Okay, so recall that what does it mean by coordinate ring of a V? Okay, so meaning you take the affine space that V live in and then quotient out by the ideal that define this polynomial. Does it make sense? Okay. On the projective side, we are more interested in quasi-projective variety here. Okay, so it's the what's quasi-projective again? The open subset, okay, of your projective variety. Okay. In there we can define what's called a rational function. Yeah, rational function. So rational function might not be everywhere defined. Okay, might not be everywhere defined here. In particular, usually we look at the regular rational function. What does it mean by regular rational function here? If it's regular at the point, it means that at that point, there's a representation that you can write as f over g. Okay, such that g of that point is not 0. Does it make sense? More importantly, in the projective case, right, we want this fi here to be homogeneous, again, to be homogeneous in the numerator and the denominator, such that their degree is the same. Okay, we don't simply take, this is a bit different from the function field of KV, if you notice. Okay, it's a bit different of KV, K bracket V, round bracket V, is a fraction field of coordinate ring of V. There's no condition on homogeneous degree of the numerator of V. And then these two will induce a map on the algebra side. So how does it induce? It's called a pullback. Okay, pullback. Okay, so you can see that this induced map here work the other way around. Okay, if your f is going from V to W, then your f star here is going from KW to KV. Okay, why? Because if you think that G is a map from W to K, right? What does this f do here? Okay, this f star here is induced by f. F go from where to where? Go from V to W. So this one go from W to K. This one go from V to W. How to compose them? Do which one you should do first? V to W first, and then you do W to K. then this composite is a map from V to K. Okay, so it's a map in K, V here. Okay, so similarly for the function case, function field case. And then there's one thing I want you to bear in mind is this two relation here, one-to-one bijection that we've proven here, induce the equivalence between these two categories. Okay, all the property that we proved suggest this equivalence. Okay, so if you forgot what this equivalent is, just think of what kind of property we've proven for them. Okay, those property you collect them together, those are called the equivalence of category. So meaning, if I gave you a algebra set here, what is the K algebra that relate to it? Is the coordinate ring? Is the coordinate ring. And then if you have a function here, okay, between R5 variety here, what is the function between the coordinate ring? Okay, F star. Okay, and then you need to check certain property, which are, for example, the functoriality of F star. Okay. Very special case one is the isomorphism here. So what do I mean by two isomorphism here? What does it mean by, what do I mean by this? Can you recall a definition? What's the isomorphism in the category of algebras? What's the isomorphism in the K algebra? Well, in K algebra, K homomorphism, right? So it just means that this K homomorphism is bijective. Okay, how about this isomorphism here? What does it mean by a polynomial map to be an isomorphism? Check or not. What is it? Sorry? So this is a G. So where should this G come from? Can it be a random G or not? Sorry? Yes, it has to be a polynomial map as well. Okay. It's not enough to just look at bijective polynomial map. Okay, because bijective just says that your map is injective and surjective, but it doesn't make sure that the inverse, whether the inverse is a polynomial map or not. If you still remember the example I showed you last time. Okay. This is a bit like homeomorphism. Homeomorphism is also like that, bijective continuous map, but not enough. We need the inverse to be continuous map also. Okay, so this is a polynomial version of homeomorphism. That's why we create these words. Okay, otherwise we don't need to create the word. I will just say, oh, bijective polynomial map, but it's not enough. Who knows the inverse is another polynomial map model, or bijective continuous map is not enough. Okay, who knows the inverse map is continuous or not? Okay, so that's why we create new word here. Okay, so this is a continuous. It's like a homeomorphism in the topology. So this is the isomorphism. On the other side, okay, on the other side, we also have a similar equivalence here. Okay, so you should imagine a similar story here. So on one side, you have a category of irreducible quasi-projective variety with dominant rational maps. Okay, so we spend some time on the dominant rational map, if you can recall. This is to make sure that we can compose, okay, such that we have a make sense making sense the rational maps after we compose. And then this also induces the equivalence on finitely generated field extension of K. Finitely generated field extension. So what's the field extension here? It's just that this K here is sitting inside this the larger field. That's it. Nothing special. No AA2 are not worried. Okay. Even if you have, I already translate for you. You won't realize. Even if I need AA2 stuff, I'll translate for you. Okay. Okay. So in this case here, we have a birational equivalence relate to isomorphism here. So birational equivalence just says that the birational map has a inverse of birational. And such that when you compose together, you get identity. Before that, you should have polynomial on inverses. Okay. Birational equivalence, you have rational map on inverses. Does it make sense? Okay. So how to apply this? How to apply this is another story here. So if you look at PNK here, projective phase here, we can cover it using the UI. Okay, remember the UI we use zero we did in particular in the first few weeks, right? So you can cover it. So meaning you can write your projective space as a union of these open set. Actually, these are open set. You can show it. And then yes, last week we briefly talked about this thing here is homeomorphic to ANK. Okay, each UI here is homeomorphic to ANK. So you can see that this AN, right, mesh up with the PN there. But not that when we define PN, right, it should be living in a larger space. Right or not? AN plus 1. Okay. And equivalence on AN plus 1. But if you look at just this special cover here, which we call the standard affine covering. Okay. So why is affine here? You can show that it's homeomorphic to AN. Okay. No, not only homeomorphic, actually that map that we gave to homeomorphism, right, is also a birational map. So actually it's a birational equivalence. So here very good. Topology you got. Okay, Zariski topology you also have. No, sorry. You have the Zariski topology, you also have the birationality. Okay, no? So it's a very nice connection. Okay, so you can jump between these two then. Okay, obviously it's under birational equivalence, not the polynomial equivalence. It's not the isomorphism. Polynomial isomorphism. So this is the isomorphism of function field. Okay, so you can write down they are isomorphic as a function field here. Again, by the category equivalence there. Does it make sense? Okay. Not only we can talk about affine covering, right? We can talk about projective variety that sit inside one of the covering. Okay. So if you have a projective variety sit entirely inside one covering, right? You also can have a birational equivalence to an affine variety also. How to see it? Okay, you just intersect with this UI as well. Okay. So you might ask, hey, he's saying, something got problem, UI sit inside AN plus 1, not AN. How to understand this UI? How to understand UI? Sorry? Play 3D? There's no 3D here, there's a random D here. Well, I mean, from the first equivalence, right, you should know that how does UI sit inside AN already. Okay, you just take basically what I write here, x intersect UI here, it means that you take your x intersect with how you know this UI inside one of the AN. That's it. Okay. Does it make sense? Does it make sense? Does it make sense or not? So x intersect UI should be living inside PNK, right? Okay, but you know how to go from you know how to map the whole UI to ANK. So for sure, the small part of UI, you should know also how it lives in AN. Maybe there's one word for you to show. Okay, why is it an R5, right? Is it necessarily close or not? Okay, maybe there's one thing for you to show there. Okay. Another thing is inside this projective variety, we can also look at the quasi-projective variety sitting inside. It's just an open subset, okay, inside this projective variety. And we say that probably we will do it in the tutorial that you can see that it is birationally equivalent to affine hypersurface. So what is affine hypersurface? Basically just affine space, just a zero set of one equation. So how to do that? We need a Noether normalization here. Okay, so this is how it is useful in geometry. Okay, so meaning what? From this connection here, actually, all these all these arrow, right? We can just reduce to look at quasi-projective variety. Okay, so from these arrow, right? Basically, we can just look at rational map on all these, no matter if alpha variety or projective variety, you can just look at it on quasi-projective varieties. Okay. Okay. So far this is the mind map I work out. I cannot say it's super complete, but at least I hope it give you some idea on what we have been doing. It's not separated, it's connected. Okay. Okay. Any question? Okay. So actually last week I missed up a very important topic here, which I jumped to next part. So actually I haven't told you what is the regular function of quasi-projective variety yet. So what is it? So it's the same. Okay, it's the same what you had in the affine case here. So let me see. Yeah. Okay. So it's really the same. Okay, it's the same definition we had on your uh, affine case, right? So you define what's a regular rational function. Okay, if it has a representation of g over h, such that h of p is not zero at that point, and then you define the domain of definition. Okay, similarly, you can define what's a local ring here. Okay, you define what's the maximum ideal. Okay, so there's one typo, okay, appearing in assignment 4. I've corrected, so please download the new version for your question 1. Okay, and then next part is this part here. Okay, so this is something that you didn't see before because this proposition here relate what happened in projective case and affine case here. Okay, so suppose V is wait. So suppose V is an irreducible variety, okay, with V living inside, not living inside, okay, on the zero set of Vx not here. So meaning what? If it is living inside the standard affine covering U0, then we can relate the stock. Okay, we can relate the stock on P at P. Okay, via these two. Sorry, we can relate the stock on the P. Okay, at the affine V naught and at the projective V. Okay. So how to prove this? You have to follow from the isomorphism that produced by the standard affine covering. Why? Maybe we can talk a little bit about this because since your tutorial, I mean your assignment is showing something stock here. So how to define stock? How to define stock here? There are few ways to define stock. In this course, you already see 3 ways actually, including the way you see in the assignment. There are 3 ways to define stock. Okay, so one way is what do you do? Very standard stock here is you just get regular function at P. If you want to look at the stock at P, that's it. Okay, you just consider all the f, okay, in your function field such that f is regular at P. That's it. And then second definition you see is this is an element in a localization, okay, of KV also, the coordinate ring of P. Okay, so if you want to ask about localization, you need to ask yourself, oh, what's the multiplicative set we consider here? Okay. And then third one that I asked you to show in the assignment is it is a pair. Okay, what's the pair? It is an open set with some regular function, I think. Yeah. So it's so here you just say that regular and P, right? But we have shown that dom F is actually open and dense. So we use the dom F. Okay. We pair F and dom F together. Become an element. Because you could imagine that, or if we can define on an open set dom F, right? Obviously, I can define it at a smaller open set also, right? So is there any difference or not, these two F? So this is the question. Okay, any difference between these two F or not? Okay, so in that definition will show you that there's no difference. As long as they are the same in some intersection, then you can try and attach your F together. It's the same. Okay. Yeah. Right. Yeah. So this is the another definition I told you just now. I'll write it as a localization. But this is a projective case. Okay, so you can see that this SV here is a graded ring. Okay, and then you need to consider MP here. You see, the MP here is slightly different from the affine case. You need homogeneous addition also. Okay, so when we discuss about projective um, similar definition theorem, then we need to add in all these appropriate adjective into it. Okay, graded, homogeneous, so okay, right. So we could define ring of a regular function. Okay, similar, very similar. Okay, just that we change the object that we define on. Okay, I want to talk about this module stuff. Okay, in retrospect, right, actually I should introduce this first. Make our life easier. We don't need to do what vector space over ring. But I didn't know that that confused you a lot actually. Okay, so one technically, I mean one difficulty is all of you come from a different background. Okay, let's say that if all this class just come from my AA1, right, for example, maybe they will know my language better. But if you come from different background to learn these things, right, maybe you already see more advanced stuff, right? Maybe you even see more already. Okay, so maybe you are not used to it. I'm not blaming you, just that maybe in future I'll try to make it more, say, 规范掉 huh? More standard, yeah, more standard. Okay, in this case here, let's introduce module then. Okay, so what's module here? Okay, so module here basically, you need to know how to compose, okay, between the element in your module and how to compose your element with a ring, okay, R here over R. Okay, when we say module over R here. It's an abelian group, okay, together with a multiplication map. Okay, usually we call it scalar multiplication. So this scalar multiplication here, what you need to do here is you need to tell people how you distribute. Okay, is it associative? Okay, associative with your the multiplication map is associative, and then the unit map. That's it. Okay, so morally it's just a vector space over if you disregard uh, the uh, the field you use in the vector space. Okay, replacing field as a general ring. Okay. So why we need these? Later I'll show you. Okay, so in this case here, you can see that if we define an R module to be finally generated, that means you can write all your elements as a linear combination. First thing is this theorem here. Okay, maybe I think you guys have seen this in your assignment, right? So you can prove that every finitely generated R module is algebraic over R here. Okay, since we have a limited time, right? So wait, how about let's jump to assignment. Wow, let's see assignment. Okay, So actually I did some adjustment to the mark here. Because I initially I thought it's trivial to prove question one, part one here, given what you have done. Okay, but actually it's not. Okay, because the one I want you to use, right? The statement that I want you to use is if A is a field and then contain in an affine domain, then A is algebraic. Okay, I thought you can use this, but turns out that you need to show this A is a field, so you cannot use it. Okay, so I mean, in this case, it's the B here, lah. Okay, so actually you need to show B is a field even before you show that it's an algebraic. Okay, so you cannot use it. So you need to do some other things now. Okay, so what's the things you need to do here? So you only know that A is a module over B now. Yeah, so in this case, let's say it's a module since you already defined it. Then you really need to work with this expression. Let's say you can express your B inverse in this case. Okay, because A is a field. Okay, so inverse should exist in A at least. Okay, but it's not clear that why the inverse live inside B. So one trick here is you use the determinant if you follow the books. Okay, if you follow the books use determinant. But some of you just use a basis representation. Right? They just use basis representation. Okay. Yeah. So yeah. So what do I want to say here? So what I want to say here is there's no one way, okay, or one way better than the other to solve it. Okay, maybe you can solve it fast, solve it slow, but you will see that different, okay, maybe different technique will involve, okay, to show these questions. So that's why these are the assignment question. No? Okay, so usually my assignment question will have different solution. Yeah, from the student. Right. How about second? Actually, I have to talk about this second question here. There's something you miss here. You didn't argue that why there exists a change of variable. Why must it exist? Okay, you just do some change of variable. Okay, and then you say that since the previous degree n doesn't disappear, it's non-zero. Then after you do a change of variable, also shouldn't disappear. It's actually not true, right? It is not true. Huh? In general, it's not true. After you do change of variable, maybe the degree D term could disappear. Maybe they could cancel out. The other possibility is your field could be finite characteristic, such that after you do, can you imagine after you do change of variable, maybe the number become 2. Maybe this C, let's say, this C become your characteristic C field. Then C will become 0. Okay, so you need to use the infinite property of this field. Okay, to say that, or you can always, okay, you can always adjust such that you can find a alpha I here such that the coefficient, okay, for xd term here is not. Okay, you need to use the infinity property. You can always adjust because the zero set is always finite in the I mean in the polynomial case, it's always finite. So you found one polynomial that's 0, right? Okay, then you just alter a bit. Such that it's not 0. Does it make sense or not? Because your 0 set is always finite, but you have infinite term for you to play, infinite element for you. And so you just adjust a bit. So this is the main point I'm looking for this question. 3 here, 3, yeah, 3. So 3, so how do I recognize whether you got read tutorial or not? How do I recognize whether you got read tutorial or not? If you don't read my tutorial, then you will just follow whatever the books say. But you didn't notice that there's some measures that we already did in the tutorial. Okay. So try and go back and read the tutorial, right? Go back and read the tutorial. For example, this part you can use tutorial already. Okay. Yeah. Yes. Maybe you can show me later. Maybe you got other reason. I forgot already. Okay. Does it make sense or not? Okay. So if you just follow the books, then that means you didn't read the tutorial. Okay. Some of the problem were you solved in the tutorial. Okay. I thought we solved more problem. Actually, it's not. So that's fine. Life is like that. Okay. For part 4, right? For part 4 here is if you have part 3, right? Actually, you can write it in this form here. Okay. Then you need to argue why your this yi cannot exist. Okay. You need to argue why this yi cannot. Because it has to be a field. Okay. Because these yi are algebraically independent. Some of you use a transcendental. It's okay, I let you go. We didn't define it. Yeah. Okay. Any question? Any question? Hey, so how about I test you some formatting here? Did you see any formatting problem here? You see, this b equals to this, right? Usually it's hard to read. Okay. To prevent it separate, right? What we can do is we can make it centralized like that. Yeah. So this is one of the consideration when you want to make this centralization of equation. Okay, no, maybe the equation is quite long. Okay. So please take note when you type your project. Any question? Any question on the part 1, question 1? Any questions? Okay. Then Nakayama, no need to discuss. Quite short. So one difficulty about this assignment, right, actually is one difficulty about this assignment is we have a lot of split result, and then you want to put them together. Okay. Let's say if you are the one who solved this from 0, how would you solve this? Let's say if you want to solve this one from 0, from nothing, would you use the same way, or would you build another way? Okay, how do you start? Okay. So when you think about this, right, then you will think, oh, why people do step 2? Why people do step 1? Okay. Why step 2 is important here? Because we want to find the monic polynomial. So when you think that, oh, can I replace this or not? It's equivalent to asking, can I find this monic polynomial different way without changing variable or not? Okay. Does it make sense? Okay, so since this name bear a name, right? So meaning people, the smart people already think it for a long time already. So most probably it's quite hard to solve. But if you can produce a shorter one, why not? Why not? Doesn't matter. Okay. Provided you have enough time and enough brain power. Not brain power. Okay. Battery. Okay. Right. Let's give me a few more minutes. I want to cover up to something first before we break. Okay, so in this case here, we will define what's called the Noetherian module here. Noetherian module is such that all the submodules are finitely generated. Okay, some module here, maybe sometimes you can think of ideals. Okay, ideals. If you think of R module R here, for example, okay, R itself is a module. Okay, then you can think of ideal as these are submodule here. So all these ideal are finitely generated. Yeah. Lemma here is if R is Noetherian, and then M is a finely generated R module, then M is a Noetherian module. So this is very similar to what we did last time. Okay, showing what? Showing yeah, so showing the polynomial in n variable is Noetherian, right? Okay, so this is very simple. Right, finally generated. Okay, so meaning you looks like a polynomial. Okay, so the proof here is quite tedious. Let's pass it. And then, okay, and then about this theorem. Okay, I want you to read this theorem and this proof, but I'm not gonna read for you. Okay, go back. I want you to read this proof here. If V is a projective variety defined over an algebraically closed field here, then every regular function on V is a constant. Okay. This is what last time we phrased that this is an equivalent theorem you have for your bounded holomorphic function. Okay, if your function is bounded holomorphic, it's a constant function. Okay, so this is an equivalent algebraic result here. The proof I saw is quite long. Okay, and then uses the Noetherian module stuff. Maybe we could find a shorter one, but this is one of the results I want you to remember. Okay, so if you look at OV here, so what do we call this? A structure shift. Yeah, structure shift on projective variety defined on algebraically closed set here. Then basically there's only one type of function you could see is a constant function. Okay, so this is related to your complex. Okay, so probably this is one of the instant why the Gaga theorem exists. Okay, how to relate complex analytic geometry to algebraic geometry. Okay, any questions so far? Any question? Okay, for those who come late just now, next week we have a talk. Please come and attend here. Okay, especially for the 2309. Okay, please come. If possible, maybe we can try and make connection with the speaker, meaning your FIPA could work towards similar related topic here. 2304 cannot already, right? You guys already picked your topic. Yeah. Maybe if you like, maybe master. Still got chance. Okay. Please come. Yes. 好，肚子痛哦，it's okay。没有啦，只是做一个 announcement 一下。And also, we will have a dinner. I will bring him go and have some dinner, so you could join as well. Huh? Lunch? On the day we have a class, right? 12 to 2. Is it 12 to 2? Monday? Yeah. Morning. Okay, okay. Then never mind. Then you just come to a seminar. Yeah. Try to talk with him. Okay, if you can. Try and ask what he doing, and then what's the current research field here. So he's doing postdoc in Sydney now. He was previously in IHES. You guys know conservation? Conservation? Oh no. Why? Who me? Who? He? He? Why he come here? I guess he is trying to transit to somewhere else. I guess he's doing transit if I'm not wrong, but he's also visiting his family and also visiting me as well. My friend, my classmate. We did undergrad together. Yeah, and then PhD we have the same supervisor also. Same year finish. So we can count as an academic brother. Same father, academic father. Yeah. We graduate together. So after graduation we split up. So I came to SMU. He went to Paris. Okay, so please come. Try and see what's the fun maths. Okay, what people are currently doing here. Okay. All right. Let's break until 5:10. 他会打扮，有老婆。
写了个 use tutorial，然后扣了我1分。
啊？
你就写了个 use tutorial，然后 result，然后扣了我1分。
啊，不够。
这1分只是因为我没有用 tutorial 吗？
想一下，不要想一下，不要紧张。
没紧张，我只是疑惑。
我听到你的疑惑了。哦。
代表了我基本上是抄书的。
对。
这是你扣1分的原因。排名重点不是你扣
确认
1分，重点是我想知道 why you 扣我1分。
对，给我确认一下。因为有时候有其他东西。
OK，
给我确认一下。
其实还想问下上面的1分是扣在哪了？
我觉得是
是什么？
因为跟书太像了。
哎，好吧。如果是个原因，我解释。
好吧，
这边呢？为什么？
你接着就好啊。
这边是，我不太懂你这句话写。
You need to choose a problem， 因为就是 like，
program
就是你怎么选到你不会有零？你怎么选到？你怎么能够做到这件事情？
因为如果它是0的话，它就不是最高词了，它就有一个更低的次数，成为了新的最高词。
又怎样？
所以这个最高词前面的 coefficient 一定是 non-zero。
不是，你有 proof 了吗？你有 proof 吗
就
？Change of variable 它的 degree 会 preserve 吗？你 proof 吗
OK，
你的意思是说 change of variable 会 preserve degree？应该是不会 preserve 的，因为你可以选到一个
这个 m to the power b 应该是 preserve 的，如果只是从这一步到这一步。
有啊，就什么？
因为我这个地方带的全部都是
带，你带进去，但是怎么知道那个不是零？它可能是零，你要选到它不是零。
OK，
对吗？
是，能解释一个怎么选？
给一个例子啊，想一个例子。change of variable 过后，那个最高吞不进去的。
有没有最高到不见？我不觉得会误见哦。
会啊，
我怎么感觉书上就是这么写的？
会啊，
我 feel 不到。
给个
书上不也是你的 solution 不也是这么写的吗？
你要读那英文字，你不能看 equation 罢了，你又中那个招，读一下那个理由。重点在哪里？重点不是那个 equation，重点是下面的解释。
哦，我解释讲，如果change of variable 我不看后面的那个 subtraction 的话，它是 homogeneous 的。
看懂了吗？
它是
看懂了吗？
homogeneous。所以就讲，只要我 coefficient 的 polynomial 我不选它为0，那我的第一 term 会存在。
OK，
什么不选它为零啊？
就我的那个 alpha 的话，好吧，不选它为零，它就会第一 term 就会存在。
你 prove 过没？它应该不能任意 alpha i 吧？
对，
应该不可以
就讲
任意啊。
后面就要
它
选
就算不为零，也有可能，它凑起来变零去，也有可能。哦，哎哎，you are right, you are right. 哎，is it? Wait, let me check. I didn't change it. Yeah, you are right, you are right, you are right.
所以 x
就变成 x，就变 x。
那一题我其实不懂 x function field and question field。
Yeah，我看看。Yeah, should be x.
It's not the whole
So,
place.
the thing is we're talking about FM variety, like so our open sets are always dense, right?
I find variety. Oh, open says. Yeah, sure. Yeah, that's right. That's right. That's right. That's right. Because it's an open set in the irreducible
好像是
base.
I asked for for extension.
So fast?
Yeah. 不是以莉迪亚的名义，以我自己的名义。
我有
没有，因为我们明天晚上
考试，
明天晚上要 CS，然后我又要考 complex，所以我们一致 OK，所以我们一致要求延期。
一致要求延期。
因为一致是一致2309，一致正版。
来2009要延期，
这个星期会死掉。如果你拜五，
是不是要延期吗？看2304的也要。
你问 master 啊？
马上全都生病了哎。
我们传到你生病了，
他不是上正课的，上正课的人。
你是当口译了。
反正我知道 Justin 是病从没来。
这一题我少写个有点错。
我的建议是 next Monday or Tuesday。OK。
其实
OK，
为什么
好，等一下。
其实这一点 B 零是不能有 inverse 的，
鸡蛋。OK，
因为 B 零属于 M 是一个 ideal，而且不是 unique ideal。所以如果 B 零有 inverse 的话，这样子 M 就会是 unique ideal，就
等下，给我改这个，再来玩几下。
改
我改一下，我要玩几下。怎么不进去？这么丑。找到 AV。 什么？你的什么？
啊，
这什么东西啊？
看一下，
这么？等一下，等一下，我先开始先。你是要问的？
没有
OK，
没有。
等一下啦，等一下，上课先。So there's a extension request because due to CS community service and assignment. Should we extend it to midterm on Friday? Yeah, I mentioned about midterm. Yeah. So okay. So do you want to extend? Okay, let's not talk about topology here. So so algebraic geometry assignment extend to next Tuesday. Tuesday. Okay. Tuesday. Hmm. FP 的 AP 那题，怎么招生做到这样头痛呢？等下我们再讨论。Okay. Well, let's see which one should we do. Okay. Let's talk about product. 啊，没换。Let's talk about product of projective. Right. Okay, we didn't really do a product of alpha variety in class, but I asked you to do in tutorial. Okay, so for alpha varieties case, it's just a setwise product. Okay, setwise product, and then you show that it is actually a variety. Okay, it's irreducible. But in this case here, how to define products here in this case? Okay, so for example, how should we define a map between P and K cross PMK to P of sun and K? Okay, so let's say I want to take 2 points here. Okay, in the projective space here. Okay, so how should I cook up with some point in some other projective space here? So what's the n here? Should it be n plus m? Lydia, what do you think? What can I do here? Sorry, how? How to combine these two together? Oh, you mean plus dot dot semicolon like this. Like this right. Is this well defined or not? Is it well defined? Yeah, is it well defined or not? Well defined. Why not? Why not? You could ask a simple question, right? So why not? Huh? Anyone want to answer? Want to give a shorter example, is it? Okay, what NM you want to take? Like this, 1, 0. P1, P1 already not good. Let's try. So 1, 0 and 2, 1. Okay. After this map, it become 1, 0, 2, 1. Then, so let's consider 2, 0, and 2, 1 is the same point. Are they sending to the same line or not? So 2, 0, 2, 1. Are they multiple of each other? So here must be time 2, right? But here time 2 still good. But here time 2, right? No, not good. So how? Okay, so you actually notice here there's a multiplication problem here. So this map cannot run away from multiplication. Okay, so what we're gonna do here is what we consider here is you take all the possible product between Si and Yi. Very large thing. Okay, so you basically take all the possible product between Xi and Yi. Okay, in this case, what's the combinatorics here? What's this number n here? What do you think? For those who are taking combinatorics, you must be good at counting, right? This is n plus 1 times m plus 1 minus 1. Okay. So you take all possible combination between I and j. LCM? What do you mean by LCM? LCM of what? LCM of what? You can try, I'm not sure, but it's called a Segre map. Is it Segre? It's an Italian name. I'm not sure I pronounce it rightly. Segre. That's become an Indian name already. Okay. Segre. Segre map. Okay. This is an Italian name. Actually, you see a lot of Italian mathematician in this course here because at one time it's really advanced in Italian for algebraic geometry. Okay, so well, similarly, we should define. We should check whether whether this map is well defined or not, correct or not. Okay, and then we need to show that actually it is a projective variety. So what we're gonna show is what we're gonna claim is. So let's put this claim here. The image, okay, the image. Let's call it sigma here, big sigma of this small. Let's call this a map small s and m, depend on n and m. The Segre map here. Segre map. And this image here is what we call the Segre variety. Okay, Segre variety. And one thing we want to show is actually there's a bijection. Okay, so let's organize this proof here. So what's the property that lies inside here actually? So let's claim, even before that, actually this Segre map here provide a bijection. Okay, on its image here. So meaning what? Meaning this image here really see the product as a set, as a set. Okay, you really see the product here. Hey, sorry, it's bijective. Okay, second, okay, it is irreducible. So meaning it is a projective variety. Okay, so very nice. Maybe you ask, is there only one way to do it? I think maybe not. But I'm not sure. Probably this is the smaller n you can put it in. If you can find a smaller n, then the map will bear your name. Okay, sorry. If you can find a smaller n, then maybe that map will bear your name already. Oh, I think this is a smallest end so far. Okay. Okay. So far, okay. I think we won't go into details, but I will tell you what is the important things to look for here. So meaning there's this map is bijective, right? How to show bijection here? Yeah. How to show bijection here? Well, I mean, can you write it as variety or not? So meaning, can you write down any homogeneous F such that it vanish? Okay, look at this coordinate here. Look at this coordinate here. Is there any equation these coordinates have to follow? Can you imagine or not? What are inside these coordinate here? Maybe you have x0, x1, right? And then maybe at some point you have what do you have? What else you have? X1, Y0 maybe got, right? Then maybe there's some other combination, right? Let's say X1, Y1. Okay, I picked some possible one for you to play already. Can you see any relation between these four? Joel. These four form an equation or not? Something else? Does it form equation between these four? Or check. Yes. Okay, you use the fact that it is commutative. Okay, then you can see that this four coordinate here form an equation. Okay, so you can similarly consider for the all the other terms. Okay. Yeah. So actually it is a projective variety on a projective space quotient out by this function. Okay, quotient out by this function. Okay. Does it make sense? Okay, so that's all I want to talk about this question. Yeah, and then other thing is quite technical. You need to go into it. Okay, but that's the map you need to start with. That's the homogeneous function you want to look at. Okay, does it make sense? Okay, so this is the example of I gave you a parametrization. Okay, can you try and see what's the implicit function that you satisfy by these zero set? So it's a zero set of what function? Okay. Okay. Next. Irreducibility part, I will put into tutorial also. Yeah. So I guess this part I think is not projective variety yet. Is it variety? Okay. Just name it as variety for now. Okay. And similar thing is you see in did you see in tutorial? No. So if let's say V and W be a projective algebraic set, then the product, okay, V cross W is also a projective algebraic set. Projective algebraic set. Okay, so what's the relation with before? Before you show that the two space product to get another projective variety. Right now here is just a subset, okay, subset of your projective space. Second, if both of them are irreducible, then the product should be irreducible also. Okay, remember in the topology, what we similar thing we show? We show that product of two connected space is still connected. Okay, so this is similar property you had on irreducibility. Do you reckon irreducibility is very related to connected or not? Irreducible you cannot write as a union of two proper closed set, right? But connectedness, those two set, the intersection is empty. Okay, so actually connected is stronger. Okay, no, connected imply irreducibility. Okay, so you have a product of irreducible space is still irreducible. Okay, so this is a product in the category if someone interested in. Okay, up to here. Next up, I want to do blowing up in details. Okay. Okay, so we'll introduce the blow up as a rational map. Okay, a rational map. So I'm gonna do this in detail because this is a subject I'm interested in also. Okay, let's spend half an hour on this blowing up. So what we're gonna blow up is we're gonna blow up a surface at the origin first. Okay, let's blow up a surface or the area at the origin first. So what does a blow up means to you? Just by English. Let's imagine first. Balloon, okay, good. Very good example. You are inflating something, right? Okay, blowing up. 有其他想法吗？金生？打球？炸平？炸平 why? Oh, explode. Okay, so you mean explosion. I thought you mean clearing out the space. 炸平啊 yeah, so what? Oh, blow. 炸平啊，炸平。I mean, if you are trying to clear out the space, I don't think this is the right thing, huh? George, yeah. Yeah, 变平, yeah, understand what you said. Just that I want to say that destroying something, I don't think is what this blowing up trying to say. Okay, I mean for this blow up, I'm sure. OK， 金生呢有没有马六甲的理解？我要听来自马六甲的理解。马下大有吗？没有没？没有啊，没有哎。是哦。extend, yeah, good. Extension. 很好. Yeah, extend. Yeah. Okay, so let's see how we extend stuff. So first we will consider a closed subset. Okay, of the quasi-projective variety here. So I didn't tell you what is a subset, what is the quasi-projective variety, but I'm gonna write it for you now. So what's this closed subset here? Let's call it AK2. A2K here, okay, with tilde. Okay, it's defined to be a set coming from a product space here. Okay, which is A2 cross P1. I guess this space is really important for blow up. You have to remember here. So we don't simply take all the points, we just take the points such that xt1 minus yt0 equals to 0. Okay, so this should remind you about the Segre method. So this sentence here actually hide quite a few details here. At least two details is hiding here. What are the two details here? There are two details here. Just judging from this line, there are two details that I haven't explained. What are the details? This should be a discrete math problem. It's not an algebraic problem. No algebraic geometry. When I say closed subset, right? So you need to show that why this A tilde is closed. Another thing, why that product space is quasi-productive variety. Okay, the second question is an exercise is hard shown. Okay. I think close should be okay, right? Close because it's a closed set. Okay, but why is it quasi-productive? Very good question. See, maybe I'll put inside tutorial. So that's why we introduced product variety just now, okay, on projective variety because we need it now. Okay, we need it now. All right. Next. So if I project onto the factor, the first factor, okay, A2, okay, this will induce us a surjection. Surjective morphism. Okay, let's write down what's this surjection here. So let's call it pi. Pi from A tilde here, going to A2. Okay, so if I say this is surjective, right? Lydia. Surjective means what? I gave you any point, okay, on A2K. Can you tell me what's the inverse image? Okay, so we want to find the inverse image of all the point in A2. What do you think? So this have something to do with this defining function here, or defining polynomial. Yeah, sorry. Sorry. Same condition. What do you mean? There's some obvious point you can try first, right? You try some point first. What are the points inside A2K, for example? Very obvious point. Start from the obvious thing first. The easiest point. For you, 1 is easier. 0, 0, eh? Okay, so let's try 0, 0 lah. I mean, from start, right? Maybe you don't know how to break into cases, so you should try some cases first. Okay, let's try some cases. Okay, let's say 0, 0. Okay, if 0, 0, what kind of xy that satisfy the equation? If you put 0 in here, 0 in here, so what are the T1, T2 that satisfy? Anything, huh? Wow. Okay, so what you get here is 0, 0 cross with the whole line. Okay, projective one space here. How about the other points? Let's say 1, 0 lah. Put 1, 0 here. Then you can put 0, 1 here. Huh? Can ah? Can ah? You can set your T1, T0 as 0, 1. Can or not? 一乘零零乘一嘛 Can, huh? How about put 0, 2 leh? 0, 3 leh? 0, 4 leh? Meaning 0 times any lambda also live inside there. Okay, the whole line live inside there. So in general, okay, in general, you can show that if it is non-zero, your pre-image is just xy plus the line that this xy live. Make sense? Very what? Chaos.
You use equal.
Oh, let me think how we solve this problem here. Wait, let me think. Oh, I think I get what you say, but let me think. You mean like this? Okay, yeah. Okay, if you want to be pedantic, I think this is all. What did you say? What did you say? Okay, so basically, if you fix a xy here, for x and y, one of the non-zero, probably you need to take t1 to be y and then t0 to be x to solve it. Okay, can you see that y, the whole line is inside there? So if you try and scale your y and x, you can see that it's still 0. Okay, if you scale your y, if you scale your x, it's still 0. Make sense? Okay. Okay, so this pre-image of 0 is a very special thing. So this is what we define as the fiber. Let's call it E. Okay, why is it an E? E stands for what? E stands for what? Elephant. Okay, this E is a projective line, which is called the exceptional line. Exceptional line. Or sometimes we call it a exceptional curve. Okay, you will see the books. Or lastly, we will call it an exceptional divisor. Hopefully, when we go to a divisor chapter, we'll see it again. We'll see it in the singularity chapter, and then probably we'll see it in divisor. So I think we only have time to do 2 more subtopics. Okay. Okay. How about the other point? Okay, so how about the other points? Let's look at what does the other point do. Okay, so if you look at for all the other xy, those are non-zero. Okay, we know that the pre-image pi inverse of xy is actually this specific point here. Okay, I think in this case, I can solve, okay, or not? Can I solve? I want to solve, can or not? Let me solve, okay? So there are actually 2 meanings, okay, 2 meanings of this pre-inverse. So it depends on you want to see this pre-image as a set or at some point, okay? But in this case, we don't have ambiguity, okay, because there's really one point in this pre-image here. So what do we have here? So actually, pi is a birational map, okay, with the above inverse, okay, because this pre-image only really have one thing, right? So actually it's a well-defined function. Okay, so you can go from xy and go from where to where? Go from xy to this point and go from this point to that point. Okay, does it make sense? Okay, no? Okay, there's only one point this pi inverse didn't define, right? Where is that point? Yes. Yeah, so that's why we split this up. Well, only at this origin it defined different. Okay, so what does this pi is giving? So hence pi actually gave an isomorphism. So last time we say that a map is birational if there exists an open set such that they are isomorphic. So what's the open set here? So actually this open set here is in between A2 throw away the origin, and A2 tilde throw away the exceptional divisor. Okay, these are the two open set. They are isomorphic. Okay, makes sense so far? So far, okay? Okay, so this is a birational map with inverses. Okay. So what is this A2 here? What is this A2 here? So this A2 here is another surface. It's another surface, which is called the blowout. Okay, so to blow something up, you need this A2 tilde. Okay, so this is a blowout of A2K at the origin. So what's the picture? How does the picture looks like here? How does the picture looks like? So you should think of the projection map, right? So you project onto A2K here. Well, let's say your origin is here. And you map down from pi of this A something coming from where? A2 cross P1K. Okay, so how do you think about A2K cross P1K? How do you think about R square? Every R, you attach a real line, right? So that's why you got a plane, because every point you have a line. In this case, every every A2 point you have a P1. It's like a three-dimensional space. Correct or not? What do you mean by 很丑? I mean, like, you got an A2, right? And then you put a P1 on every point. Oh, so how your P1 looks like? Okay, so your P1 is like a open out fan. I don't know. So on every point you have these opening out fan lah. That's it lah. 就这样. Yeah. That's right. Correct or not? That's right. That's how you think about it. That's right. Correct or not? So R2, right? R2 is like every point you have a R. So you got a plane. So in this case, if you think about it, every A2 you have a open out fence. Yes, that's right. Okay, so a point inside here is a point on the A2 plus a direction. Okay, plus a direction. Make sense? Okay. This is better than R3. R3 only got one direction only. Okay. Yeah. That's another problem. Okay, let's not discuss about that problem. Yeah, there's another problem actually. Yeah, there's actually some other problem, but let's not discuss about that. Okay. Yeah. No. Your problem is your P1 sitting inside R3, but now A3, but now this is not the case. This is like I don't know how it attached, but no, don't care yet. If you want to do that, right, you will have a different product already. Maybe you have some product here, different product. You are viewing P1 in R3, which is what suggests in this picture, but in reality, right, at this point, when we zoom into this point, you really only have an R2 inside there. We don't know how this R2 sit inside R3. Sense? Okay. Otherwise, you can ask a similar question here. How about my ask like this? No point, right? No point to do this. So in this case, you can see that actually there's a so this is a change of basis, right? So you should also think about change of basis there. Yeah. Okay. Make sense? Okay, makes sense. Okay, good. Very good question. Yeah, this is where fun max comes out when we try to change bases whatsoever. Okay, so this one is it. That's it. Okay, but how the pre-mesh looks like? How does the pre-mesh looks like here? What do you imagine here? Okay, maybe we give some idea. Maybe let's not do proof. We do draw you some diagram that you imagine. Then maybe the proof is easier for you to read. So for example, let's not just look at this point, right? Let's look at a line that contains this point. Okay, let's look at a line containing this point. Okay. So what have we shown? What's the pi inverse of this line here? Huh? 0 cross with what? The whole P1, right? Okay, cross with the whole P1. So it's like if you use the fan description, it's like this. Okay, there's a fan on this 0. Okay, but instead of thinking about fan, we prefer to think about it as a line inside higher dimensional space. Okay, we call it a projective line, P1. Okay, we think of it as a line. Okay, does it make sense? Make sense or not? Okay, we think of this space here as a line. 是吗？是 line 吗？ Last time we proved that this is a S2, right? Okay, it's a line, a close-up line. Okay, so we think of it as a line. Sorry, circle, yeah, circle. So the line will cross together. Okay, so we think of it as a line here. Okay, so there's pre-mesh of this 0 is a line. How about the rest? How about the rest? How about the rest? How about the rest on this line, red line here? It's just some point in the A2 cross P1. Some point. Just some point. Make sense or not? Okay, just some point here. So for example, let's pick some point for them. Let's say this is the point. Okay. Just some point. It's not the whole line. It's some point on that line. Okay, if you like, I draw their line picture here. So you just pick up some point here. So if some of you have do advanced maths, right? It's like a section. Okay, you are picking section. Okay, from this bundle here. Okay, so on this, is the color too similar? Maybe change a bit the color here. So about what one? Okay, so from this product space here, you just pick one point. But at the 0 point here, you have the whole line here, projective line. Okay. So far, makes sense? Okay. Okay. Right. So let's play this game here. Maybe this proposition will suggest why we do the blowout like that. So let L mu be the line through the origin in A to K here. Okay, given by this formula here. XY in A to K. Lx minus mu. Okay, what did you observe here? What did you observe here? What did you observe here? Hey, this is a calculus thing. This define a line. Can you check? Y equals to ms plus c. That becomes this form here. But c here is origin, right? So c disappear. Okay, but ms plus c, meaning what? Ms there, you can distribute the m, right? You can distribute the denominator, for example. So if you consider all the line here, right, it's all the possibility of Lx. But this one is really similar how we define the blow up, right? Is it similar or not? Is it similar to the blow up thing? Similar, huh? Okay, so this L lambda mu here is actually consider all the possible line that passes through the origin. Okay, let's draw it. Be something like this, like this. Okay, we look at all the possible. Okay, so if you zoom into a certain line, if you zoom into it, okay, and then look at what's the pi inverse of L lambda mu here, what is it? Actually, it is a exceptional divisor, okay, because you always pass through the origin, plus the pi inverse of L mu, take away the origin. And remember that our pi inverse only defined on point other than the origin. And then you need to take the closure. Okay, the what closure you take here? Zariski closure. Okay. So there's a proof for this. The proof actually is not hard, not too hard. Okay, but this statement is actually quite surprising. Okay, how to think about this statement? So if you take another line, okay, let's say we take the other line, right? Okay, what do we have in the pre-image of pi here? We still got this line, okay, plus some other pre-image of these points. Okay, like that. Sorry? Say again? What's the blowing out part? So blowing out part, where is the blowing up? Blow up, blow up, blow up is a subset of A2 cross P1. Yeah. No, we haven't defined other blowout yet. We only define one kind of blowout. There's a blowout at the origin. That's it. So what is a blowout in the origin is a subset of A2 cross P1 such that this sorry, it's a zero set of this ST1 minus YT0. That's it. All the point that satisfy this. Okay? All the point that satisfy this. So you mean how to imagine this? What do you mean? You mean how to draw this? There's an extend. Oh, okay. Yeah. So you see, here, okay. So this guy live inside, let's say, three-dimensional, 2 plus 1 here. But you see, extend what? Extend this, what we call the base space here. The place where we project. Correct? Okay, you can see that this line here become a line plus another line. Extend this point here to an exceptional divisor. Does it make sense? Okay. Actually, this line has a very nice picture here. So if you okay, maybe we just focus on talking about this theorem. Next time we'll talk about example. So if you look at this picture here. Okay. So you can see that if you look at all the line that passes through the origin, and look at the pre-image. And look at the pre-image here. Okay. All these pre-image are at the point 0 that contain this exceptional device. Okay, all these pre-image contain this exceptional divisor as the pre-image of 0. Okay, so can you recognize why these has gradient or not? Why this line has gradient? Why this line has gradient? Okay, let's say this L lambda mu, the pre-image is here. Okay, so how about the other lambda mu? Right. So you can see, so this is right, this like this, right? So it's like clockwise, right? Is it clockwise? Let me think. So up. Anti-clockwise. Anti-clockwise. I mean, okay, wait. Depend on how you see this, right? Is it depending or not? Does it depend? Let me think. This seems to suggest some clockwise or anti-clockwise. I think there's no difference there because you can clockwise here or anti-clockwise here. Doesn't matter, I guess. Yeah. Doesn't matter, right? This, I mean, they do it like this because you imagine if they extend it, they're gonna cross, but actually there's no crossing, right? Yeah. Any question? Any question on this picture here? Or if you want to ask why different line, huh? Why different line? Why different line? All the pre-image share this accessible divisor. How about these? How to get this pre-image here? Just now, how do you get pre-image? We have a formula, right? Pi inverse. What's that formula? You get this xy and then xy plus the point where this xy, the line that xy lies inside. I don't know. Xy, comma xy, and then semicolon sy. Okay. I don't know. So let me ask you a question. If you have a different xy, different lambda I, lambda m, is the same xy satisfied or not? Huh? Meaning, for example, I give you a picture here. For example, this one is for L lambda 1 mu 1. This one is L lambda 2 mu 2. Okay? The point that satisfies this equation here, same or not? Same or different? Can pick one only. Huh? Different line. You see from picture, cannot see me? Yeah, different line. Yeah, must be different, right? Okay, so meaning what? So if you send it back to the pre-image, it must be different also. Okay, it must be different also. Does it make sense? Make sense? Okay, makes sense. Any question? No question? Any question on this picture 有没有什么遐想？你问 ，sorry，是因为那个 bijection, yeah, it biject on the, yeah, you can think about it using that way. So because it's a bijection away from what is it? From the origin. Okay, so if you pick point from the origin, other than the origin, then because these are different points, right? Okay, so their pre-image should be different. Okay, but I guess one thing you need to think about is how they sit inside this A2 cross P1. How they sit inside there. We already know they are different, right? But can it be like one here or not? Like, what's the any rules that can see how, I mean, if there are difference, okay, how the difference in the let's say let's call these base space. How they're different in base space, does it affect how it sit on this let's call this bundle thing, this product space? Based on the map, the inverse map. Okay, so how do you imagine this? So for every point, let's say on this lambda L lambda 1 mu 1, right? Okay, so all these points obviously we will attach like let's say x1, y1 like that. Okay, then when you get sent up there, okay, if you send it up there using pi inverse here, you'll get x1, y1 with some direction. Okay, with what direction? X1 dot dot y1. Okay. But similarly, okay, if you pick other points on this line, right, you will send to a different, let's say x1i, y1j. But the line they send to is the same. Does it make sense? You know how to imagine this? One coordinate change, the other coordinate constant. So if it is in R2, it's what? It's a constant, it's a graph of a constant function. Fair enough. So this part here keep changing, right? It's a line. But the other part is the line that this point is staying. But the point you pick from come from the same line. Yeah. So they are constant in one direction. So in the projective line is a constant. So it's like 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0 like that. It's constant in the third coordinate. Yeah, right now. So this one is in A2 cross A2 cross P1. Okay, so in this part is a constant. Okay, in the other part is this one, right? Okay. Okay, constant, but this constant change, right? This constant change, right? Okay. So let me finish up. So you can see that this constant change, right? What's this constant? This is a line, right? How do we identify line in P1 last time? Exactly using this lambda and mu, right? Which is the gradient. I don't know. If you rearrange these, what is this? You'll see in a more familiar form. So if you see in a more familiar form is what? Y equals to lambda over mu x. Y equal to mx plus c. So lambda over mu is the point of P1 here. But these are different points, right? Because these are different lines. So these are the different point on P1 now because this line is 0 cross P1, right? This line here. This line here. So it's a 0. This line is a 0 cross P1, right? Okay, so there's a P1 coordinate on this line. So all these lines sit in different coordinates, although it's a constant in P1. Oh, does it make sense? Make sense? So what is this C? I can write down this formula C already. Actually, it's lambda over mu. Okay, if mu is non-zero, if 0, then you. Yeah, so meaning that line will be. Okay, so can understand why this lines get split up. 李弟啊，吹起来了啊！我们已经吹起来了，看到怎样吹嘛？看到怎样吹嘛？看到怎么吹嘛？为什么会被吹起来？ It's blown out by the gradient. The gradient differentiate all these lines. And then why got direction? Because this direction are the direction given by it. Okay. Okay. 好，我觉得已经算最美了嘛。
那哪一篇？
哪一篇？
在他们那群转的那个。
哪一个？哪一个宣传 actually, how should think about this 给我几支笔。乖乖，不会吧？我就不用乖的。So you go one direction, right? Then you go the other direction, right? And then go. 可以帮我转一下。说什么了？And then Yeah. 你看你过来，Yeah， 真的没有转完，再弯一点，不可以回来那条线，Yeah，OK，OK 吗？前面就好了，前面就 OK 吗？Yeah，
零上面一条线，那意思。
What do you mean by 零上面有一条线？How do you think about it? I'm talking about this space now. I'm not talking about this space. I'm talking about this space. Yeah. This space. Uh-huh. It's like the fans the fan right? 有没有人带扇子来啊？ So if you open out the fan right, and then you can how to say put it vertically, but you remove the dot. You remove the dot. Then you remove the connection at the bottom, such that they can open up. 有没有人带扇子来 destroy 呢？ I mean, if you extend it infinitely on both sides, fair enough. Yeah. 可以折啊，可以折不 Should I do it? Should I do it 啊 Should I do it? 几点了 6:06 啊 Are you guys want to leave? Or you want to see? Did you play this fan origami when you are young? You guys played this before? Your fan 啊讲一点在一起啊，用 blue 点，用 blue 点。See? Right. Yeah, So you see, this is the fan, right? Okay. So consider all the line, right? Pass through the. Let's say this is the origin in the middle, the bottom here, right? Okay, but now you're gonna because these are coming from different lines. Okay, different lambda over mu, right? So they are different point on P1. Okay, so in the third coordinate, they are in a different point. Okay, but at the same time, we don't care about this the origin here because this origin here is not just origin, right? It's the origin from the whole line. Okay, so you should imagine that all these lines just stay on the constant P1 line. Okay, so it open up. Make sense? Because this point here is not just a point. In this case, it's a point, but in that case, we have the whole E. We have the whole E. Okay. And then all the other point is there on the constant C there, which is the C over mu. So this differentiates the height. Okay, so meaning what? Meaning what? So if I pick one line, what's the pre-image here? It is this thing plus this whole thing here. Okay, this is what this pre-image talking about. Okay, understand? In particular, you also have this point out because this point line inside the pre-image of 0, 0. Okay, and then all the rest is the pi inverse on this one. On the L lambda mu take away 0. Okay, so it's a T. So this T is like this side here, this side. So if you look at this pre-image, right? What's this part here? This part here. This is the line containing that point. Okay, so if you look at pre-image of that line, all these points should live in the same line. But what determines this line? if you remember, what's the bijection ratio? Why is this a line? From first week, how do we determine this is a line? Why we call P1 a projective line? It's 1 to 1 to S1. What S1 is that? You use what? Use the gradient. This gradient number is fixed for every line. Okay? Lambda and mu fixed. Then this gradient will fix. Example. Okay, so if this gradient change, then your height in this P1 change because it's a point in P1. Okay, so for example, this one, okay, let's say this one is x, this one is y, right? So here is here is gradient 0. Okay, let's say gradient 0 here. And then when your gradient increase, right, to infinity, right, when you're close to vertical line, so your gradient increase. Okay, how about the other side? Then decrease. Okay, simple. Okay, so this is just the blow up on the surface at the origin. And next time, you should imagine that. You see, whenever we do affine space, projective space, right, we want to look at some subset, zero set. So meaning we also can put a subset here. Okay, we'll put a subset. Maybe there's a dragon here. Okay, maybe there's a dragon here. So let's draw this. Maybe there's a dragon here. After blow up, how does this dragon become? Maybe we want this dragon. Okay, never mind. Dragon only pass to 0. Okay. So if this dragon pass through here, right? What's the blow up dragon here? Can imagine? Can imagine or not? Lydia, you must imagine. How do you imagine this? If there's a dragon here, I blow up what? Or how does the dragon look like? How does the dragon looks like? Wait. 没有这样难啊 These are just a point on this line You already know how the whole line looks like. You just connect the dot together. You just get the dot together. What you get is a flying dragon. Correct? You just connect the dot together. It's an isomorphism, Jingsen say bijection Correct? I just pick one point from this line. I already covered all the point other than 0 in this plane. And then this is just some point from this plane. So you just pick this point. Okay, look at the image. This point, image 2 point, 2 image. And there. Connect them together. Okay. 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 So see you next week.